Hello everyone, my name is Stephen Gigrich and this is Lab 5, Faraday's Law. As an overview of my lab report, I will first introduce the lab and the physical principles behind it, as well as go over my lab setup. Then I will go over my lab procedures, observations, and calculations. Next, I'll go over my code and its outputs, and I will end it off by answering the 2 questions of the main ideas of the lab. Introduction. Background information and physical principles. Here we have the equation showing Faraday's law, which states that EMF is equal to the negative of the number of turns times change in flux over time. And Lenz's law, it looks very similar, but it's slightly different. And Faraday's law explains how much current is produced, while Lenz's law helps explain which direction the current is produced in. The theory of superposition is that fields can be added together to create an equivalent net field. Vectors are widely used in physics to convey multi-dimensional information and consist of a magnitude and direction of a quantity, and current, where the key idea is that electron flow is equal to the negative of the current flow. The purpose of the circuit lab was to increase our understanding of Faraday's and Lenz's laws and the relationship between the change in flux, the induced current, and the resistive force created. A secondary purpose of this lab is to get more practice using GlowScript and Python and how to effectively create a simulation that relates to real life. Here's my lab setup during the experiment. As you can see on the left, I'm holding the magnet above the opening to the aluminum foil tube, and then on the right picture you can see that it's at the moment that the magnet just hits the ground. And using the video and the frames, we were able to find the time between these 2 events. Here's just the quick calculations, finding the difference start and time between the 5 videos, then adding them up to find the average, which I found to be 1.206 seconds. Here are the systems and surroundings of my experiment. The system of the experiment was the earth, the magnet, and the aluminum foil tube, and the surroundings of the experiment was everything in the room and any other metals near the magnet that might affect the induced currents. To preview my experimental results, the simulated time matched closely to the real time, the direction of the magnet doesn't matter, and the effects of Lenz's law are pretty cool. Lab procedures and results. Here are the steps to complete this lab. 1. Acquire the necessary materials, which are a bar magnet, a roll of aluminum foil, a scale, and a meter stick. 2. Using an app on your phone such as PHYS, determine the north end of the magnet and mark it with a marker. 3. Drop the magnet down the tube of aluminum foil. Record on your phone to get time of drop and repeat that 5 times. Measure and record the length and width of the aluminum foil tube. And 5. Measure and record the weight of the magnet. Here are my observations from the lab. The magnet fell significantly slower than if in free fall outside of the aluminum foil tube. After entering the tube, it wasn't just that the Lenz force slowed down the acceleration, but directly countered it, and the force of gravity resulting in constant velocity. And 3. Falling through the tube took the magnet 1.206 seconds. Some possible sources of error were bad recording, wrong measurements, incorrect code, and a flawed magnet. GlowScript. Here are 2 functions used in my GlowScript code. The first one takes in a dipole moment and a distance and gives you the dipole, and the second one calculates the flux given a magnet and a ring. Here's the output of my code. On the left you can see the tube that the code produced as an image, and on the right you can see the graph of velocity versus time and the code output, where in the simulated world it took 0.247 seconds. Questions and answers. Some assumptions I made during this lab was that the magnet was flawless, the aluminum had no resistance, there was negligible air resistance, and that all the measuring devices were accurate. So to answer the first what if question, if the conductor was reduced, the resistivity of the conductor was reduced, then the resistive force would decrease as well, and so the magnet would fall faster and approach falling normally in free fall due to gravity. And the second question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would disrupt the flow of the ring currents and reduce the material available to produce resistive currents. Thus, the magnet would speed up as more holes or slots were added, eventually approaching no tube being there and therefore it approaching free fall.